Okay, so this next graph is the graph f of x equals the sine of 1 over x. So here's the third case in which a limit does not exist, and that would be when, as x approaches a certain number, in this case 0, the function f of x oscillates so much between two values that we can't really determine any specific value for that limit. So this is kind of widely spaced for the graph, but I did my best. So in this case, the limit as x approaches 0 of f of x, I'll just write f of x, does not exist due to this specific oscillating behavior. However, there are certain functions, I'll just draw it over here. So this function won't have a specific equation, or at least that I know of, but it would. But if we had something that say looked maybe like this, then we would have a limit at x equals 0. Because as we can see, the curves are getting smaller and smaller as they approach that limit, which in this case would be 0. Should probably label this one g of x. So the limit as x approaches 0 of g of x, this equals 0. Because this function is actually approaching a limit as x equals 0, while this one doesn't approach any specific function, in specific value. So those are the three main cases in which you might not see a limit. And then, so in my previous video, if you recall, I showed you how to find the following limit. Limit as x approaches 1 of x squared minus 1 over x minus 1. And we couldn't use direct substitution on this because that just gave us 0 over 0. And we can't really determine anything from that. So what I showed you was that we can simplify this function. So actually we get x plus 1 times x minus 1 over x minus 1. And then we would just find the limit as x approaches 1 of x plus 1. And then that we could directly substitute 1 in. And that gives a limit of 2. So even though there was no defined value for 1 on this in this function, it still approached the limit of 2. And so another example that we might see would be something like, say, limit as x approaches, say the square root of x squared minus 9 minus 3, 4 minus 4 over x. This will be limited as x approaches 0. So in order to to solve for something like this, well, we obviously can't plug in 0 because this will be undefined. But when it comes to radical expressions, we can rationalize it. And that would be and we would do that by taking taking a radical numerator here and multiplying it by its conjugate. And then we do this to both the numerator and the denominator, just so that this cancels out to 1. So it's just a different version of the same function. As x approaches 0, so we get x squared minus 9 minus 16 over x. I'll just put the whole thing in parentheses. Times x squared minus 9 plus 4. And then we could just simplify it from there. Yeah, part of it. X approaches 0. And then we would just simplify that by rationalizing it, or actually we don't really. Yeah, we kind of do. But we would just simplify this by rationalizing the denominator. So to save time, I won't spend too much time on that, and move on to our next concept, which would be basically the rules for evaluating limits. So all of these rules will be based on, it's basically just direct substitution. So basically what we would use for direct substitution in this case would be things like the limit as x approaches c of a constant a, so a being a constant function, would simply be a. Because if you're to think about it visually, a constant is just a horizontal line. So, approaching from both the left and the right of C, it would just be approaching whatever that constant value is. And then another one would be the identity function. The limit as x approaches C of x is just C. Because again, this would just be a diagonal line with a slope of 1. Or just to sketch it really quickly. So if this value is C, then based on what we know of the identity function, the limit as x approaches C for this function would just be C. Okay. And then the final one that we have would be the limit as x approaches C of x to the n, which is basically just x with a positive, x to the power of a positive integer n, which, similar to the identity function, we would just plug in c to the n. So those are the more basic ones. if we were to apply this to other, to more complex things, then we would have things like the rule for addition and subtraction. The limit as x approaches c of two functions, f of x plus or minus g of x, because for this rule it doesn't really matter. So I guess before I show you how that's evaluated, let's just say that the limit as x approaches c of f of x is just L, and the limit as x approaches c of g of x is, let's go with n. So for this we just have the limit of f of x, which we defined as L, plus the limit of g of x, n. Alright. So basically, if you have two functions that are being added together, the limit of this larger function would just be the limit of the two individual functions added or subtracted together. So next, what we do about multiplication. The limit as x approaches c of f of x times g of x. Well, that would just be L times n. Yeah, so as you can see from these two examples, all this really is just direct substitution. We're just basically saying f of, basically just taking whatever this limit is and substituting it for the limit as x approaches c of either f of x or g of x. So next comes division. Just like with addition, subtraction, and multiplication, it's just going to be L over n, but there is one thing, there's just one thing. N cannot be 0, because then this limit would be undefined and we'd have to figure out something else. And so for our next one,